we're going to determine whether or not this 0.896 for our correlation coefficient is sufficient for us to represent that data as a straight line, then we get to do a hypothesis test on that. Now, since R came from sample data, this looked like there are six people that we randomly chose to do this study. Remember, English letters like R indicate sample statistics, and when we go to the population, then we use Greek letters. When we're doing a hypothesis test, we have a null hypothesis and an alternative hypothesis. Okay, the Greek letter rho, say it, rho, is the population parameter, okay, for this correlation coefficient. So in our hypothesis testing, every single time in every example, we're going to do a two-tailed test. We are going to let the null hypothesis be that rho is 0, meaning there's absolutely no correlation at all in that data, okay, positive, negative, or otherwise. And so then we're testing against that, okay, that it's not equal to 0. So I'm going to say a strong correlation here. In our hypothesis testing here, our degrees of freedom, all of these are going to be a t-test. Sorry, I'm fighting with this tablet in front of me. And on all of them in this section, our degrees of freedom is going to be n-2. So our test statistic t that we find relies on r. We have to find our r value first before we even do our hypothesis test. And it's r times the square root of n-2 over 1 minus r squared. So let me see if this is legible to do it this way. Okay, sure. Our number of 5, 6, 7, number of values here, we had 5 ordered pairs. So that means our degrees of freedom is going to be 3. Our alpha, let's say that we're told that we want alpha to be 0.05. Okay, that'll be given to us in the problems. And so if I have a two-tailed test, level of significance 0.05, degrees of freedom 3, when I go to my table F, my students' t-distribution, we find out that those two values are plus or minus 2.571. Okay. If you want to draw yourself a picture here, and label those points, my pen will write that small. So then we find our test statistic t, which is 0.896 times the square root of n-2 is 3 over 1 minus 0.896 squared. If you type that into your calculator, you get 4.512. When we compare that 4.512 to our cutoff, our critical region, we see that it's to the right of 2.571, which means it's in our rejection region. So we're going to draw the conclusion to reject the null. If we reject the null, I gotta type because I'm about to get carpal tunnel here. If we reject the null, that means there is sufficient evidence. Maybe there's sufficient evidence to conclude that the coefficient, let's say that there is a strong linear relationship. Maybe make that a touch bigger. we do not reject the null. That means we're accepting that rho is 0 or close to 0, and therefore there's no correlation. So here we have a strong correlation or a strong linear relationship with this data. This means when we get to the next section and we want to find the equation of that line, we can proceed and we can go ahead and do that. So looking at this next example, our one that seems like a very strong linear correlation in the negative direction, we'll do the hypothesis test just to make sure. My pen is being very strange today. There it goes. And again, for our hypotheses, they will always be equal 0, not equal 0 when we're testing our rho, which is the population parameter for our R, our sample, Pearson's R. Let's also let alpha be 0.05. Actually, let's go with 0.01 on this one, which will be different than what I prepared, so I'll have to flip through and look with you guys. If we count our number of ordered pairs here, there are 6 of them, which means our degrees of freedom is equal to 4. Our, excuse me, our critical cutoff values, if we have a two-tailed test at a significance level of 0.01 with degrees of freedom equal to 4, that's plus or minus 4.604. That's a 6. It's supposed to be. Then our test statistic, we're going to take R times the square root of n minus 2 over 1 minus R squared. Now officially it's negative squared, but when we square a negative, we're going to get a positive out of that. Now the negative out in front of the 0.981 stays. This expression is a positive number, and if I hit the buttons right in my calculator, at home I got negative 10.113. And if you still like to draw the picture here for our situation, and your author shows, he explains and puts a little table in there, a little blue box, I think, that says you have to meet these criteria to be able to do this. Populations have to be normally distributed, we have to have random sample, we have to have, be sure you read through those stipulations. I kind of skirted past that in these examples. Okay. But the negative 10.113, it's down here. It's in our rejection region. So that means I can go straight to saying reject the null hypothesis. Okay, there is enough evidence to conclude a strong negative, we could use the word linear, correlation exists in this population. So, and that's our goal. Sometimes in the hypothesis testing chapters, sometimes we wanted to reject the null, and sometimes we were glad that we didn't have to reject the null. But here our goal, I mean, we can't move forward, we can't say our data is worth doing much with unless we can reject that null hypothesis. That indicates that we have a strong enough linear correlation at the 0.01 level of significance that we could continue and we could think about this data being linear. All right, and because our R value for this blob of numbers, it was so low, it was less than 0.5, that's really not even worth doing a hypothesis test on. Okay, anytime your R value is less than 1/2, when I say less than 1/2, I mean in magnitude, so between negative 1/2 and positive 1/2. Okay. If you wanted to do the hypothesis test on this, you're welcome to do that on your own time, and you should very much draw the conclusion that you do not reject the null, meaning that there's not a strong enough correlation for us to go forward. So in the next set of videos, we'll talk about how do I come up with that equation of the line.